Our industry sponsor is Fetch AI, a company focusing on artificial intelligence and blockchain. They are developing a software framework for autonomous economic agents, or AEAs. AEAs are agents which act independently of constant input from their owner and autonomously execute actions to achieve their prescribed goals. Our initial direction was to use the AEA framework to investigate the use of AEAs compared to a centralized algorithm for solving problems. This was a very broad direction, which made designing and scoping our project a large task. We brainstormed different ideas, had discussions with Fetch AI, and learned about the AEA concept. In the end, we decided to create simulations investigating the concepts of emergence and cooperation.
In our simulations, there are random water locations with limited water in the environment, and the agents are free to seek and extract units of water in a fixed pace from the water locations. Each agent consumes water daily and will die if it runs out of water. More features such as message communication and water sharing are used to deploy some of our strategies. So here's our question to answer. How does Fetch AI's autonomous economic agents, also known as AEA, help our daily tasks? We believe it's done in multiple dimensions, including quantity, collaboration, and dispersed information sharing. The idea of quantity matters is inspired by the story of USSR's interceptor MiG-25. The idea of collaboration is inspired by the prisoner's dilemma, and the dispersed information sharing is inspired by Frederick Hayek's dispersed knowledge. We don't have time for the specifics of our intuition, our experiments, and the social implications of our findings here, but you can find them in our report. Basically, we come up with this conclusion. We believe the AEA framework has the potential to accelerate many of our daily tasks because it can unite objects and have them work for the same goal, allow agents to communicate and approach social optimum by breaking the prisoner's dilemma, and utilize dispersed knowledge during cooperation in a decentralized manner.
To implement the project, we initially divided the team into 3 groups. This division was intended to simplify work. Each group would only need to know the technical details of their domain. Blanche, Olaf, and Trun formed the simulation team. This is the largest and most technical group, focusing on understanding the AEA framework and implementing the simulation logic. Tancred and Kevin formed the visualization team. This group focused on visualizing the simulation output in a way that is informative, clear, and friendly. Greg was responsible for the simulation analysis and project report. He would understand the function of each component and work with the rest of the team to organize our investigation.
The system is broadly divided into 2 parts, simulation and data analysis. A user can specify simulation parameters, which are then passed to the simulation subsystem. The subsystem creates log files, which can then be used for data analysis. The simulation subsystem itself consists of 2 types of component, the environment and the agents. The environment keeps track of the simulation state, so things like how much water each agent has and the agent positions. It then passes these informations to the individual agents, who communicate amongst each other and finally tell the environment what they want to do.
Pygame was the logic library to use for visualization, as it is the best way to manipulate simple shapes. We then have 2 Python files for visualizing the data. The first one recovers the data and transforms it into Python objects, while the second one loads the objects and uses them to update and display on the screen.
The statistics module takes a simulation log and shows a series of graphs summarizing the simulation. It includes statistics interesting for measuring individual survival, collective survival, and disparities between agents.
We used Git for software version control. Our project is currently on a public GitHub repository, including documentation describing usage and design. The project has been packaged so that all components can be used through a single command line interface.
The system has been tested extensively. We have thoroughly unit tested the physics engine of the simulation, and to make sure that all the pieces fit together, we did integration tests in addition to that.
Now a demonstration.
During the visualization, the grid is hidden so we can see agents moving smoothly around the map, Agent's life is represented by the agent's color going from green to red, while we can see the water pits decrease in size if their water is drained.
Looking at statistics for this simulation, the top left graph for the proportion of agents surviving shows an interesting pattern of stable periods followed by collapses.
In general, we consider our work a success. For visualization tools, our code is robust and concise. The main coding task also went quite smoothly. The report was done in a bit hurry, but we managed to find a suitable framing question as the theme of our report.
I learned that dedicated project management is an important part of delivering a project on time.
We would have liked to go deeper into the simulation strategies, but I'm very proud of what we achieved. In these unusual times, we managed to have great solidarity and teamwork, especially in these last few days.